Okay, so now we're going to put this all to work. Okay, so we're going to draw a sketch, and any good sketch starts with a carefully drawn pair of axes. And since this picture is quite important, I'm going to really take the time to use a ruler and make sure this is done carefully. There's no point in rushing this just to do a sloppy job after that much work. Right, so here we got the origin, label the x and y axis carefully, and now we'll begin. So what you're going to want to do is start with, where's my other page? Start with the easy stuff. Okay, so go through this, almost go back to the beginning, and this is where it's going to pay off that we identify the conclusion from each step, because you don't want to have to now retrace your steps through all of the details. So the domain was all real numbers, so our domain is everything. We don't have to worry about any domain restrictions. We have our y-intercept was the origin, and these were our two x-intercepts over here, right? So we've got basically these are our intercepts that we need to worry about, because this one takes care of the y-intercept. So let's plot these. Let's start with that. We'll plot those points. So we've got the origin and then the point -4 on the x-axis. So origin's kind of already plotted by default, because I always do that, but I'll just exaggerate it in blue just to make it clear that it's actually on the graph. And then -4, where's -4 on here? Well, I haven't picked a scale, so I have the freedom to just do this. There it is. There's -4 on the x-axis. Okay, I'm not going to go -1, -2, -3, -4, -5, and then go 1, 2. Like if you do that, it just makes your graph actually, paradoxically, it makes your graph harder to read if you add those details in. So it's best to just be minimal at this stage, but be consistent, right? Be careful and as consistent as you can. It's not going to be 100% perfect because you're drawing it by hand. How could it be perfect? But I'm not. If I were to put -5 way over here, that would be bad. Or if I put -10 right here, that would be pretty bad. Or if I put -5 over here, that'd be even worse, because that'd be just an outright contradiction, right? So try your best to beat a scale. If I were to put -2, I'd try to put it right in halfway in between, and so on. But it's not going to be perfect. Okay, so that's 2 points from the intercepts. So start with the easy things to pick off, right? What about part C, when we looked for any asymptotes? If you found any asymptotes, you want to plot them immediately, especially vertical asymptotes. Horizontal asymptotes too, though. In fact, I shouldn't. I regret already saying especially. Plot your asymptotes immediately, because you're going to want to know that they're there, and it'll make everything else go more smoothly. But we didn't have any vertical asymptotes, and we didn't have any horizontal asymptotes. But when we did calculate the end behavior of the function, and we found that the function grows upwards without bound on either end, right? On both ends of the x-axis, the function grows upward. So, but we don't know how at this stage. We don't have enough information. So why don't we just do this? Just go like this. And notice I'm using pencil, because this might change. I'm with the understanding that I might erase those and move them. But you're just writing a note to yourself, essentially. Just remember that, as you move far to the right, the function goes upward, and as you move far to the left, the function goes upward as well. Well, we don't know the nature in which it does this. Maybe it goes up and then is concave down, or maybe it goes up and it's concave up like that. But we don't know that yet, so we can't draw this in a permanent fashion. Okay, well, that's all we get from step C. For step D, what did we get? Remember, the intervals of increase and decrease came from this table. That's what we have here, along with, well, we have a local minimum. This is a concrete point. Any local extrema you have, this is what I would do next. So from the top, identify the domain, plot your intercepts, draw any asymptotes you have, and then plot your local extrema. Don't worry too much about the intervals of increase and decrease yet. That'll happen a bit later. But if there's any concrete points on your graph, you want to take an opportunity to draw them. So f of -1 is equal to -3 is a local minimum. This is a point we actually want to plot on the graph. So the x-coordinate of -1 and a y-coordinate of -3. So where's -1 here? Like I said, cut this distance in half to get -2, and then maybe cut that distance in half this way to get -1. So I'll put -1 there. It's not going to be exact, but it's at least reasonable, right? That's what you're shooting for here. And if that's a unit length of 1, then -3 maybe could be about down here. Let's say that's not too bad. So -3 I'll put there. So then our actual point is going to be right here, and I'll make a solid blue dot for that point. Okay, so that's all you're doing. So now you can see a little bit more. We've got our local minimum there. So maybe it kind of comes down, goes through this point, comes down to a minimum, goes up, and then comes out like there somehow. But what happens in here is still pretty foggy. So to clarify as much as we can, let's move on to part E, those intervals of concavity. And actually beyond the intervals of concavity, because part of the inflection points were found in part F, those would be a good thing to have right now. Let's draw the inflection points on our graph. So one of them was the origin, which we've already got that point drawn. So this is an inflection point. Let's remember that. The other point here, let's plot this point. X coordinate of 2 and a y coordinate of 6 times the cube root of 2. So for an x coordinate of 2, let's just take this to be positive 1, and then this, maybe let's say that's positive 2. So I'll put that as a 2 like that. And then the y coordinate of the point is 6 times the cube root of 2. What's that going to be? Well, if this is negative 3, then maybe this would be positive 3, and then something up like here would be 6. So this is going to be a place where our graph, it's going to be pretty hard to draw a graph perfectly to scale. And 6 times the cube root of 2 is a pretty nasty number to begin with. So probably what we would do is just at this point, let's make a judgment call, and let's just label that as 6 times the cube root of 2. The more you label, the more of a license you buy yourself to be imperfect, right? And that's the best you can do. And at least this is not too unreasonable, because the cube root of 2, that's like 1 point something. And it's not going to be too big. Maybe it's like, well, I don't know what it is exactly, but it's definitely bigger than 1, and it's not too large, because the square root of 2 is 1.4 something. So it's less than 1.4, but it's bigger than 1. So this number is going to be larger than 6, but not too much larger than 6. So that's a fairly reasonable place to put it. It's not going to, like I said, it's not going to be perfect, but it's not bad. But anyways, that is how we can now draw our point. So here is our other inflection point. Okay, and now with that point being there, you can kind of see this. There's no way this is going to be part of the graph. We need to revise this. This needs to be moved. So, because the only way you get to here is if you went up like that, and then you maybe turned around and went like that, right? But then you'd have another local minimum here, so that doesn't make any sense. So let's move this maybe to over here, right? And we might move it again, or I'll slide this down to be able to see better. We might move this again. We might find that it's still not good, but at least it's a bit better, in a better location than it was before. Okay, so now we've drawn on all the obvious things, right? All the intercepts, the local extrema, and the inflection points, and the asymptotes. There weren't any, but if we had asymptotes, we would have drawn them at this stage, or we would have drawn them by now. Now you're going to go back to look at your intervals of increase and decrease. So now let's go back to step D, where we did our first derivative table, and we summarized that f is decreasing from negative infinity all the way up to negative 1. So on this entire range of points for x values, the function is decreasing. So as we move to the right, the y values of the points in the graph have to decrease. So let's do something like this. And again, I'm doing pencil again because this is not going to be permanent. I'm just doing a rough sketch. Start with that, okay? And then I'm just doing like a connect the dots kind of a thing. So it's definitely decreasing all the way up to negative 1. Is that going to be the way I do it? No, not yet. And that's why it's drawn in a non-permanent fashion. But let's finish the whole graph like this, and then we can revise it afterwards and do it a bit more permanently. Okay, what about the rest? F is now increasing between negative 1 and 0. So that's this region here, right? It's increasing here. In other words, it's just going to increase from this point to this point. So that makes perfect sense. And if it didn't, if you ever get to a point where it's like, okay, it's increasing from negative 1 to 0, except if this point were down here, then you'd know something went wrong. And you'd have to stop and check your work. So definitely go slow and carefully and watch for things that don't make sense, because the sooner you catch an error when you're doing a problem like this, the better off you are. Right? You're not going to want to catch an error at the very end of the process, and then how are you even going to know where the error is? You're going to have to go through absolutely everything again, and you don't want to do that. So go slowly, go carefully, keep your work organized, and always be on the hunt for things that don't make sense to catch them as soon as possible. Okay, you can tell I'm kind of just rambling off these tips as I think of them, but that's the way it goes. Okay, it's also increasing on all the positive x values. Right, so for all positive values of x, so for this entire half of the x-axis, the function's increasing. And there's no contradictions here. It's going to go from here up to this point somehow, and then it's going to go up after that again. So let's just draw it like this. That seems to be completely amenable to what we've already done. So that's going to be a really crude, a really crude shape of the picture now. But that's a good start. Now we're going to incorporate concavity. So now let's take a look at our second derivative table and our intervals of concavity. So where was f concave up? On the entire negative half of the x-axis, but then also to the right of positive 2. So it's concave up all the way on this range, and then all the way from here all the way to the origin. It's concave up. So if it's decreasing and concave up, that means it's kind of coming down like this. It's coming down and curving to the left, curving to the right. Right? So if it's going to come down through this point, I got to make sure I don't come, if I come in like this, that's not going to work, because then in order to come down to this local minimum, I'd have to change concavity. So I have to make sure I don't come in, I have to come in here really steep so that it can come in, still be concave up, hit that minimum, and then come back up to the origin. So why don't we actually connect these points, these 3 points first, since this is we have a little bit more guidance here. So this is going to be like, let's say it's like this. Okay, so that's decreasing and concave up. And then now this gives you an idea of how steep this needs to come in, right? If I come in like this, that's not going to be good. I need to come in a smooth way. So how about something like this? Yeah, it's not too bad. As I move in from the right, it's decreasing and it's concave up, right, all the way to -1. So that takes care of that. Now what about between -1 and the origin? Is it concave up or is it concave down? Between -1 and the origin, that would fall into this interval here, right? That would be part of this column. Between -1 and the origin, that would fall under here, and it's still concave up. But now it's increasing. Notice by drawing this in pencil, now I don't have to keep constantly looking back at the first derivative table as well. I can kind of forget about that now, because I've essentially just drawn the first derivative table's results in pencil. That's the idea, so you don't have to keep looking back at it. So now you know you're increasing but concave up. Well, that part's fairly straightforward. There's only one way to do that. It's going to go up like that. Okay, so that's the left half of the curve. Now that we've got this more permanent version, let's erase the part that we drew in pencil. Let's get rid of this. So that we don't need that anymore. So now you get an idea of what the graph's actually going to look like. And then we'll just do the same strategy on the other half. So let's look at between these 2 points. It's increasing from the origin up to this point, between 0 and 2, but is it doing it in a concave up manner or a concave down manner? And that's where we'll come back to our second derivative table. That's this region in here, right? Between 0 and 2, function's concave down. So that means it's going to be increasing but in a concave down manner. We've got to do an arc like this, an increasing but concave down arc. So how about, it's easier to draw this way than the other way around, so I'll just start up at the point and come down like that. So that's increasing and it's concave up. Okay, and now I can erase this draft material back there. And then lastly, we just need to finish this off. It's going to go up to infinity, we know, but how so? In what manner is it going to do it? Well, I think this was an inflection point. If you check back here, that was one of our inflection points, 2 and 6, the cube root of 2. This is an inflection point, so it's going to change from concave down to concave up. Or another way to look at that is just to the right of 2, the function's concave up, or that's really what we said here. To the right of the positive 2 on the x-axis, the function's concave up. So that means this is increasing and goes off to infinity, but in a concave up manner. So let's do it like that. So that's probably the most sensible way to draw this. Okay, and that does it. We can erase our draft, and now we've got it. So that's curve sketching. Go slowly, go carefully. It's really an exercise in bookkeeping and organizing and having perseverance. There's a lot of things to check. There's a lot of work to do. And it's just a matter of staying organized and keeping track of the conclusions. And I know I've said this already, but I want to emphasize it one more time. Make sure you summarize your result at the end of each of these steps, right? Use a different color to put boxes around them, because you don't want to have to now read through every single bit of work along the way. You want to just get the important bits from every step so that you can put them together to get the graph. So, and then what was this the graph of? This was the graph of, well, we had f of x is equal to x to the 1/3 times 4 plus x. I guess if I'm going to sketch the graph, I should also want to include what the actual function is. And then that is curve sketching.